Good morning, I mean to teachers and all my fellow friends. Today, we are from Book 2 and we will present the linear transformations. Introduction. A linear transformation is a function from one vector space to another that respects the underlying linear structure of its vector space. A linear transformation is known as a linear operator or map. The range of the transformation may be the same as the domain, and when that happens, the transformation is known as an endomorphism or invertible and automorphism. The two vector space must have the same underlying field. Characteristic of linear transformation T V map to W is that for any vector V1 and V2 in V and scalar A and B of the underlying field, TAV plus BV2 equal to ATV1 plus BTV2. The linear transformations are useful because they preserve the structure of vector space. Therefore, under certain conditions, a lot of quantitative assessment of vector space that is the domain of the linear transformation may automatically hold in the linear transformation image. For example, structure immediately give that the kernel and image are both subspace, not just subset of the range of the linear transformation. Most linear functions can probably be seen as linear transformation in the proper setting. Transformation is in the chain of basis formula are linear, and most geometric operations, including rotation, reflection, and alteration, dilation, are linear transformation. Even more powerfully, linear algebra techniques could apply in certain very non-linear function through either approximation by linear function or reinterpretation as linear function in unusual vector. A comprehensive, grounded understanding of linear transformation reveals many connections between area and object of mathematics. Question 1. Give the definition of the linear transformation from vector space V to a vector space W. T V map to W. A linear transformation T from vector space V to vector space W is a function that satisfies two key properties. The first one is additivity. For any vector U, V in the V, transformation T must satisfy TU plus V equal to TU plus TV. This means that the transformation of sum of two objects is equal to the sum of the transformation of the individual vector. The second one is scalar multiplication. For any vector U in V and any scalar C, the transformation must satisfy TCU equal to CTU. This means that the transformation of scalar multiplication of a vector is equal to the scalar multiplication of transformation of the vector. Question 2. List out the properties of linear transformation. Let T Rn map to Rm be linear transformation and let X in the subspace of Rn. First one, T preserve the zero vector. T0x equal to 0tx, hence T0 equal to 0. The second one, T preserve the negative of a vector. T negative 1x equal to negative 1tx, hence T negative f equal to negative tx. The third one is T preserve linear combination. Let X x1 until xk in the subspace of Rn and a1 until ak in the subspace of R. Then if y equal to a1 x1 plus a2 x2 plus until ak xk is followed that ty equal to t a1 x1 plus a2 x2 until ak xk is equal to a1 tx1 plus a2 tx2 plus until ak txk. Now I will invite Carmen to continue the presentation.
Okay, thank you, Chinali. So I will present question 3. So question 3 is about discuss the following linear transformation by giving one example for each transformation. So I will explain about question 3 part A. And question 3 part A is show about the vector. So I assume that T ratio 3 cubed equal arrow to R square. And I let the T ABC, which is 3 times 1 matrix, to the 2. And according this, we need to prove by two property as shown on the slide, property 1 and property 2. Next. So in property 1, which is T bracket U plus V equal to TU plus TV, and I show by left hand side first. And first, I will let U equal to A1, A2, A3, and V is B1, B2, B3. So in left hand side, T bracket U plus V, and we get the number at your left side, step 1. So step 2 is like this, and next, step 3 is I make it to become the property like I given just now. And finally, we will get this the final answer. So for right hand side, I will show also the same thing. Right hand side is TU plus TV. So as usual, just now I have shown you that the let U equal to A1, A2, A3, while V is B1, B2, and B3, and I get this. So next we change it to the final of the result, and we get that the TU plus TV equal to the left hand side. So for the property 2, is TCU and CT bracket U. Property 2, for left hand side, I will substitute like this. So then I get the answer is C bracket A1 minus A2 and A1 plus A3. This is for left hand side. So for right hand side, to prove the left hand side, come to the next slide. Yeah, so you can see above that right hand side, I get the same thing with left hand side. So this shows that the property satisfies the question above. So for the part B, I will pass to the Chongjia Yu. Thank you.
So my name is Chong Jia-yu. Now I will explain the TPN map to TPM, which is for a polynomial form. So first we assume that TP2 convert to T33, and then let T A plus BT plus CT squared equal to A plus B plus CT plus BT3. So first I will let U become A1 plus B1T plus C1T squared, and VT become A2 plus B2T plus C2T squared. So to prove that, we need to assume that U is that equation and V become A2 equation. Then we need to prove TV plus U equal to TV plus TU. So first, I will prove the left-hand side, which is TUT plus TVT equal to T, then we expand A1 and A2, we mix up together. So we will get A1 plus A2 plus B1 plus B2T and C1 plus C2T squared. So we combine with the coefficient of the degree. So we will expand it, we will get A1 plus A2 plus B1 plus B2 plus bracket C1 plus C2 bracket T plus B1 plus B2 T power of 3. So then we prove the right hand side, which is T bracket UT plus T bracket VT. Then in this case, we will expand it, become bracket A plus B1 plus C1T plus BT power of 3, and then plus with bracket A2 plus B2 plus C2T plus B2T power of 3. Then we combine together with the coefficient, the degree of T, then we will get the bracket A1 plus A2 plus B1 plus B2 plus bracket C1 plus C2T plus bracket B1 plus B2 T power of 3. Then we prove that it is satisfied since the left hand side same with the right hand side. So we can go to the another slide. It proves the another next slide. So to prove that T, the scalar scale, which is T K times U equal to K times TU. So first I will prove the left hand side, which T bracket K UT equal to T bracket K, we take out the scalar, and multiply with A1 plus B1T plus C1T squared. So we expand it, then we will get T bracket K A1 plus KB squared T, but KB1 T plus KC1 T squared. Then we expand and separate it, we get KA1 plus KB1 plus KC1 T plus KB1 T power of 3. Then we do the right hand side, K times TU T, which is we will get K bracket A1 plus B1 plus C1T plus B1T power of 3. Then we combine, then we will get, combine, expand it, we will get KA1 plus KB1 plus KC1T plus KB1T power of 3. Then it is satisfied since left hand side same with the right hand side. So then I will pass it to Jing Hui.
I'm Xinghui and I will continue the next question. For the question 3C, transformation of function from V to W, given that transformation of function maps from the set M 2 times 3 to M 3 times 2. Let A1 equal to A1, B1, C1, D1, E1, F1, given that the function A1 and A2 are member of V, where TA equal to A transpose. We need to prove that is a linear transformation if and only if the following two requirements are satisfied. Now, we solve the first requirement, which is the transformation of sum of vector A1 and A2 equal to transformation of each of the vector and summing up. From the left-hand side, transformation of sum of the vector A1 and A2 will obtain A1 plus A2, B1, A1 plus A2, B1 plus B2, C1 plus C2, E1 plus D2, E1 plus E2, F1 plus F2. And by transport it, we'll get T A1 plus A2, B1 plus D2, B1 plus B2, E1 plus E2, C1 plus C2, F1 plus F2. So for the right-hand side, we split into sum of two vectors, TA1 plus TA2, and transport it, we'll get the linear transformation same as the left-hand side. Thus, left-hand side equal to right-hand side. We have verified the first requirement. Next, we will multiply the vector A1 by a scalar lambda equal to lambda TA1. From the left-hand side, lambda applied into the vector A1 and become lambda A1, lambda B1, lambda C1, lambda D1, lambda E1, lambda F1, and transport it. Then by factor out the lambda from the vector and put scalar lambda out of the vector, we will obtain lambda times A1, D1, B1, E1, C1, F1. From the right-hand side, we already know that this vector is just the linear transformation that we get from the left-hand side. Thus, left-hand side equal to right-hand side. We have verified the second requirement. Next, I will pass to Shui to continue.
Linear transformation play a fundamental role in mathematics. They provide a powerful framework for representing and understanding the relationships between different vector space. Linear transformation preserve vector addition and scalar multiplication, making them valuable tools for solving systems of linear equations and analyzing geometric transformations. The study of linear transformation not only has theoretical significance but also find practical application in deserved areas, contributing to the development of mathematical modeling and problem-solving methodologies. That's all from our group. Thank you.